good evening. Probably for Artem it is good evening now.
Yes.
Our next speaker is Professor Artem Lopatin from the State University of Campinas. He is going to talk about polynomial identities for the Weyl algebra over finite fields. So, please.
Thanks a lot for the introduction, and thanks a lot for Alexei for helping to organize this conference. And so the title of my talk is Polynomial Identities of Weyl Algebra over Finite Fields. As you can see from the title of my talk, that another talk with similar title has already been presented yesterday by Carlos, who is my PhD student, who was my PhD student. A couple of years ago, he defended his thesis in Universidade, Estadual de Campinas, and now he's professor in University of Santander in Colombia. But in my talk, I will consider the case of finite fields, but nevertheless, I will have to repeat some key definitions from his presentations and even some of the results. So it's inevitable. I will try to do it very fast, but so some parts of my talk will be more or less the same as parts of the talk of Carlos. I will also try to say something which he didn't said, because I mean it's wide topic. There are a lot of things which can be considered. So I'll try to say something new, even in a case when a field is not finite. So I will start with a key definition of Weyl algebra. So it's a summary, and okay. So first of all, we have field F. It's arbitrary field of arbitrary characteristic. We'll later consider when it's finite. And here, at the moment, we don't have any assumption whether it's finite or infinite. And all vector spaces and algebras we consider over this field F, unless otherwise stated. Then later in my talk, I will introduce another field as well. So we use this usual notation. And so here is the classical definition of Weyl algebra. So it's an algebra which is a quotient of free associative non-commutative algebra into variables x and y, factored by the ideal generated by this relation. In other words, in algebra, in Weyl algebra, when we have epsilon and x, we can interchange them and write down xy, but we have to pay, and we have to write down plus 1. We have to write down plus 1. This algebra, Weyl algebra, is quite important. It has a lot of very interesting properties. It has a lot of interesting connections with other areas of mathematics, and a little bit later I will talk probably a little bit about it. But now let me consider some generalization of a Weyl algebra. This generalization is known under the name of parametric Weyl algebra, and it was introduced by Benkert, Lopez, and Ondrus several years ago, actually nearly 10 years ago. They published several papers on this subject. First of their papers was published in Transactions of American Mathematical Society, and then in other journals. So the definition is the following one. Instead of this one, we can consider some polynomial h in variable x. We just make this substitution and we obtain new definition. We obtain parametric Weyl algebra. This parametric Weyl algebra, it has a lot of common properties with Weyl algebra, and actually it can be considered as subalgebra of Weyl algebra. That is why it's called parametric Weyl algebra. But we, in our research, we didn't stop here, and actually we considered this parametric Weyl algebra over an arbitrary F-algebra B with unity. So B is a fixed F-algebra with unity. Of course, it's associative, and of course, it doesn't have to be commutative. It may be non-commutative. It may have divisors of 0, so we don't have any restriction, just the only restriction that B has unity. It's the only restriction. And here we consider the F-algebra of non-commutative B polynomials and variables as x1, etc. xm. So essentially speaking, here we can interchange elements from B with these variables or with these letters. So B itself may be non-commutative, but elements of B we may permute with elements x1, x2, xm. And so in this way, we obtain F algebra from computer to be polynomials in these variables. And so here's the definition. Definition exactly the same as it was before, but instead of the field, we consider this algebra B. And we have additional requirement for the polynomial H. Now we require that coefficients of polynomial H belongs to the center of algebra B. So we need these conditions. Without this condition, of course, we can define it, but we don't know what to do with this definition. It's really important that we have this condition. So essentially speaking, H belongs to the center of polynomials over X with coefficients in B. And we obtain this parametric Weyl algebra over the ring B. And so a little bit about motivation and examples. Well, first of all, in this, our definition, if instead of B we consider the field F, of course, we will obtain exactly this parametric Weyl algebra, which was introduced by Benkert, Lopez, and Andrews. Then, if in case H is equal to 1, let's say in this definition, in case H is equal to 1, we obtain classical Weyl algebra. Here you can notice that we use different letters. Here, this letter, and here we use another letter. We do it on purpose. Probably for this talk it's not very important, but not to mix them, okay? Not to mix them. Then if we have that H equal to 0, then we obtain usual polynomial algebra, which is quite clear. And so here is another example. So we always assume that H is not equal to 0 because we know all we want to know about polynomial algebra. And so here's the last property, which shows that normally when we consider H, it's more interesting to assume that coefficients of H do not belong to the field F, but they belong to the algebra B away, but not in the field F. One of possible motivation for the introduction of this parametric algebra is the following lemma. It's quite old lemma. It was obtained in 1988 by Van Stein, Van der Bern, and Avami. So here we consider an or extension of a field over a ring of polynomials in one variable x. So construction of or extension I'm not going to give here because it was already considered by Carlos. And this parametric Weyl algebra, it can be obtained as a result of construction of or extension when we start with a ring of polynomials. So here sigma is automorphism, delta is sigma derivation, and it's classical construction for extension. And so if we have this condition when R is, well, in classical construction, of course, instead of R, we can take just a ring. It doesn't have to be a ring of polynomials. So, but if it is a ring of polynomials and sigma is an automorphism, then this ring, or extension is isomorphic to either quantum plane or quantized Weyl algebra or to our parametric Weyl algebra. And so it's one of possible motivation for consideration of these parametric Weyl algebras. Another motivation for consideration of Weyl algebra, of course, we can consider ring of polynomials in one variable z, and consider two operations over it. One is derivation, is usual derivation of a polynomial, and another is multiplication by this variable z. And we can consider algebra generated by these two functions. And operation in this algebra is composition. Of course, composition of two derivation is not derivation in general, but we get some algebra. And in case characteristic 0, this algebra will be exactly isomorphic to classical Weyl algebra. In case of positive characteristic, it's not the case, but if we consider the quotient of Weyl algebra by relation x powered by p equal to 0, where p is a characteristic, then we obtain exactly this algebra generated by multiplication and derivation. So this is another motivation for consideration of Weyl algebras. And our work is dedicated to identities. Of course, everybody knows that while algebra in case of characteristic 0 doesn't have any identity, it's a very classical result. And we managed to generalize this result for the case of parametric Weyl algebra. So here the result is the following one. But first of all, about convention. Here we need the following convention, that h is a polynomial in X, and so h has the following property: its leading coefficient is not divisor of 0. We also, this condition is also required. If we consider parametric Weyl algebra over the field, of course, this condition is always holds. But in case of arbitrary unital algebra B, we have to require that this condition holds. Later, I will come back to this convention. And so if characteristic is 0, then this algebra of this parametric Weyl algebra doesn't have non-trivial polynomial identities. As I said, in case of h equal to 1 and b equal to the field f, it's quite simple corollary of Kaplansky theorem, and it can be easily proven. But here, well, it's not very complicated because our main result of this research was theorem 2. But even this theorem, it requires some work. And here idea was to present elements of parametric Weyl algebra as derivations. And this connection with derivation was widely used here. And so second theorem is the following one, that when field f is infinite of positive characteristic, then we need another condition. If h of alpha is not divisor of 0 for some alpha from the center of ring B, then identities of parametric Weyl algebra are exactly the same as identities of P by P matrices over ring B. And in a partial case, when B is field F, we got that parametric Weyl algebra of the field have the same identities as P by P matrices. This result is probably possible to get using some classical theorem, although I'm not very certain about it. But this result, I'm completely sure that it's not possible because this algebra B can be quite bad, and it doesn't have to have some good properties which usually are required. So these results were obtained earlier, and they were published and they were discussed by Carlos. I would like to say a couple of words about this convention, which also will show that probably it's not possible to get rid of this condition. Well, at least, okay. So here we have the following example. So which shows that we need convention. Here we have the field f, which is infinite, and we consider the following B algebra. It's algebra of so-called algebra of double numbers. So it has two generators. One is unity, then of course it's commutative, and square of the second generator is 0. So it's two-dimensional, simple, commutative, associative algebra. And as polynomial h, we can take this element. So then this convention fails. This convention obviously fails. And then we obtain that we don't have this theorem. We don't have this theorem. On the contrary, we obtain the following result. So here we can consider T-ideal of identities of this algebra, and it's generated by these two identities, F1 and F2. It's quite easy to see that because of this fact, this algebra is never PI equivalent to any algebra of T by T matrices or any F algebra C. This fact is quite easy. Well, because minimal identity for, let's say, 2 by 2 matrix has degree 4. It follows, essentially speaking, from this fact. Okay. And then just an interesting remark that actually the identities of this algebra are the same as the identities of Grassmann algebra of rank 2 or 3. Just funny result. We didn't expect it. But anyway, so it shows that here we have completely different situation, which shows that we really need this convention, which in turn show that Here, we cannot hope to rely on some general result to obtain this equivalence. But now, what about the case of finite fields? Because here we have infinite field, and it's quite important. It's quite important that the field is infinite. So now assume that field is finite. It has q elements, and so characteristic is p. And earlier we showed the following proposition. First of all, the ideal of identities of parametric algebra in case when algebra B is equal to F, so classical parametric algebra, they lie in the ideal of P by P matrices. Well, when we have this condition, but these two algebras, they are not P equivalent. So ideal of identities of parametric algebra is not the same as ideal of identities of P by P matrices. So here we have completely different situation as in case of infinite field. And that here we don't have equivalence is relatively easy to prove because by results of Genov, we know some identities for n by n matrices of a finite field for any n. So he explicitly constructed some identity of a finite field. And we just consider this identity and we show explicitly that it doesn't hold in case of parametric algebra. So we don't have here PI equivalence. And so we have an open problem to describe this T-ideal, And so here is principal result of my talk is this theorem. To formulate this result, let me first introduce additional notation. So we have finite field F, and we consider some infinite field which contains our finite field F. For example, it can be algebraic closure of the field F, or can be some other field. And for convenience, we can introduce the following notation. So when we consider K algebra, which stands the product of field K or with B over the field F, then we denote by BK. Because we're going to use it several times, so it is good for us to use this notation. And simple remark, so if we consider this parametric algebra, of course, it's parametric algebra of the field F, and consider tensor product with K, then it's exactly the same as parametric algebra over the ring BK. And so here's the result. We assume, that, of course, that H is not equal to 0. Then we have the following equality. So what do we have here? Here we have on the left-hand side, we have exactly our ideal of identities of parametric algebra over the ring B. And on the right-hand side, we have here the ideal of identities of parametric algebra now over the algebra BK. So BK is K algebra, and K is infinite field. So it's algebra over infinite field. But of course, here we cannot write down equality because here we have coefficient in the field K. But we consider intersection. We consider intersection with free associative non-commutative algebra where lies exactly this ideal, and then we'll got equality. So essentially, so it's our principal result. And it immediately have a number of corollaries. First of all, we can use this second theorem. We can apply this second theorem. So we assume that this condition holds, then we have description of the ideal of parametric algebra, and we apply this result. So what we got? In this case, we obtain that if the leading coefficient of H is not a divisor of 0, and H alpha is not a divisor of 0 for some alpha from the center, then we got that any polynomial identity of parametric algebra can be obtained as follows. We take some polynomial identity over the field K, and polynomial identity of P by P matrices with coefficients in BK, And if this identity has all coefficients in field F, it will be exactly identity for our parametric Weyl algebra. So we have this intersection being equal exactly to identities of parametric Weyl algebra. Okay, and in case of the field when B is equal to F, we also got this equality. And these results, they have a number of corollaries. But before this, I will consider idea of the proof, and then we'll consider a number of corollaries from these results. So idea of the proof is the following one. Actually, we will prove some general statement where we don't have any Weyl algebras, and then we just apply this statement. And so here in the idea of the proof, we don't consider Weyl algebras. We just consider A to be some unit of algebra, and V is just some non-zero F subspace. So then, of course, we have ideal. So here we have identities of V. It's better called identities of V, yes. And we say that these identities, they are multi-homogeneous. If every multi-homogeneous component of any identity of V is also polynomial identity of V. So what does it mean? So we have some identity. We can write it down as a sum of homogeneous components with respect to multigrading of free associative non-commutative algebra in variables x1, x2, etc. And if all components, they are polynomial identities, then we say that these polynomial identities are multi-homogeneous. So of course, in a characteristic 0, we know that any identity is multi-homogeneous, and actually if a field is infinite, then it also can be shown that this ideal is multi-homogeneous. And we have the following folklorem, which says that if we consider identities of V and they are multi-homogeneous, then we got the following description of it. So here, what do we have here? Here we consider tensor product of V and field F, field K. Field K is some infinite field which contains F, as was before. Consider identities of this vector space over the field K, and consider intersection with a free associative non-commutative algebra with coefficient in F. This folklore lemma is quite easy to prove. And then we have the following condition. Condition is the following one. So we assume that G is some polynomial in one variable. So actually here we can write down this x1 and x1, they are commutative, but it doesn't matter. With coefficient in the field with P elements, then they exist, and we assume that they exist alpha from the center of algebra A, such that the whole two condition holds. In this case, we say that this condition holds. Yes, and so this alpha stabilizes V. So when we consider the action of product of alpha and V, we still are in V. Well, here it's important that alpha is from the center, so it doesn't matter we multiply from the left or from the right, it's the same. And the second condition is that G of alpha is not a zero divisor for V. What it does it mean? It's written here. Here again, G of alpha will be element from the center, so it doesn't matter we multiply from the left or from the right. And here we have key lemma. So we have this pair algebra vector space, and this pair satisfies the above condition. Then any polynomial identity for V is multi-homogeneous. And then these two lemmas, so this key lemma and folklore lemma, putting together, they immediately imply that if pair A and V satisfy condition, then we have this equality. So essentially speaking, it shows that in this case, identities of vector space V, they can be somehow obtained from the identities of V considered over infinite field, roughly speaking. For example, we may consider some partial case when V and A is just algebra of matrices over this ring, and then we got this equality. Because here we obviously have this condition holds because it's enough to take alpha to be this element, and then it is easy to check that the condition is satisfied, and then this equality is satisfied as well. Because then he will obtain the identities of matrices over some infinite field, of polynomials over infinite field, as they are the same as just identities of matrices over infinite field. It is easy to see. Another remark which shows that this condition doesn't hold in certain cases. For example, we can consider algebra which has center equal to the field F. And then we can take this polynomial, and V is non-zero subspace, and we obtain obviously that this condition doesn't hold. This condition doesn't hold. So obviously this condition doesn't hold for matrices. So essentially speaking, for this condition to be valid, we need that algebra have big center, because if center is just field F, it's never holds. But lucky for us, in case of Weyl algebra and parametric Weyl algebra, in the center, let's say we have x powered by p. In case of positive characteristic, we have x powered by p. Okay, let me come back to this main result. And so in this case, we might take that x powered by p is element from the center, then we obtain this condition holds, and then we obtain immediately that this equality holds. So it is not. So then we obtain this result. Actually, this result have one quite interesting corollary, which I will give here. So here we will not consider many details. So it's about Lie identities for Weyl algebra. Weyl algebra with respect to Lie bracket is, of course, Lie algebra, and some people, they consider Weyl algebra always as a Lie algebra. And so we assume that F is finite field of characteristic 2. And we consider Weyl algebra A1. So it's, of course, infinitely dimensional Lie algebra with respect to Lie bracket. And then we can obtain that it's not finitely based. It's not finitely based. So the ideal of Lie polynomial identity is not finitely based in this case. Actually, we have exact description of Lie identities in this case. They're exactly the same as identities of 2x2 matrices over an infinite field F of characteristic 2. So this example of 2x2 matrices in case of infinite field of characteristic 2 is classical example of algebra Lie, finitely dimensional in this case, of an infinite field which doesn't have finite basis of identities. And this example was obtained by Vaughan Lie. But in the paper of Vaughan Lie, explicit basis of this TRDL of identities was not found. Then it turns out it was found by Drensky, but let's put it this way, it remains secret for some people from mathematical community like myself. Probably it was known to everybody else, but it was never published, and it was part of his thesis written, I guess, in Russian. And then I repeated his calculation. Okay, I used different methods, but I obtained the same result like 30 years later. And then this result can be now found in a survey of Drensky, published a couple of years ago. Survey is about weak polynomial identities. Thick survey with a lot of different results, and so its results contains explicit description of a basis of Lie identities of 2x2 matrices over infinite field of characteristic 2. And here, in case of finite field, we will obtain exactly the same identities, and the TLD of these identities is not finitely based. Okay, and so now I will consider some applications to the case of subspaces. Here, let me consider this notation. So by this, I will denote f-span of this polynomial in parametric Weyl algebra. So here I mostly will assume that ring B is just field F, and so I'm not writing down B, but at some point I will do this, but just once. And so it's f-span of polynomials of this kind. So some motivation for consideration of these subspaces, well, first motivation is, of course, with algebra, because when we have h equal to 1, s equal to 1, and characteristic equal to 0, then this subspace is exactly with algebra with respect to Lie bracket. And we have the following proposition, which shows when we can introduce Lie bracket over this space. So this case exactly corresponds to the case of with algebra in case of characteristic 0. And here we have this nice formula of Lie multiplication. In some other cases, we can also introduce Lie multiplication or Lie bracket here, for example, here. And the last case is trivial. It's not a very interesting one. But simple Lie algebra we can only obtain here. Okay. And a little bit more about motivation. This kind of motivation was considered by Karl, so I don't want to repeat it. I just want to say that Jumadildaev, he has a number of papers published about polynomial identities. Polynomial identities of this vector space, and he studied in particular standard polynomial identities and other stuff. In case of characteristic 0, he made a list of conjectures and so on. And so, as I said earlier, we can introduce here a Lie bracket, and in case here we work with one pair of variables, but of course we can expand it to several pairs of variables, and we will obtain nth with algebra. And example of simple infinite-dimensional Lie algebra in case characteristic 0, of course. In case of positive characteristic, we also have with algebras, but we should consider quotient by x powered by p. And well, okay, so I don't consider the case of positive characteristic. And so it's an important problem to study identities of with algebra. There was some research about it, and there is a well-known conjecture, which is written here. So it says that in case of one pair of variables, any polynomial identity follows from standard Lie identity of degree 5, which is written here. This conjecture, I guess it belongs to Razmyslov. But it's open. It's not known in spite of the case where... Okay, let me come back to this formula. So in case of with algebra with one pair of variables, we have this very nice formula of multiplication. And it seems that maybe it shouldn't be so difficult, but this conjecture is still open. And there is some paper about Z-graded identities of with algebra by Fredes, Koshlyukov, and Krasilnikov, where they described in case characteristic 0 all the graded identities explicitly. Okay. And so now we can apply these our results and to consider what we can say about identities of these subspaces of Weyl algebra, of parametric Weyl algebra. And so we got this result. We immediately got. Essentially speaking, this result means that we can make reduction to the case of infinite field F. And in case of finite field, we got the same as in case of infinite field F. And then considering the case of algebra B equal to the field F, we'll got the following two corollaries from our previous research. So here, the field F is arbitrary. Earlier we did it in case of field of infinite field, but here we can now say that the same holds in case of arbitrary field. So here we established minimal polynomial identity for this subspace. So it can be considered some generalization of, or some analog of parametric, some kind of associative identities for with algebra. And so it has degree 3, and then we studied in details the case of characteristic 2, and also we studied identities of minimum degree here. And so I would like to finish my talk by the following conjecture. So here we consider the case of h equal to 1. Here we consider S, and we ask the following question: when the standard polynomial is polynomial identity for this subspace? This question was studied by Jamalidaev, and in case of characteristic 0, he obtained quite a lot, so he proved actually this conjecture. But we can formulate it in case of positive characteristic, so this conjecture is given. But we don't know how to prove it. It was proven in several partial cases, but in general, it is open. So I guess, yes, there is one final thing which I would like to mention, and it's concern this key definition of parametric algebra. So when you hear something about generalization of Weyl algebra, probably the first algebra you're going to mention are so-called generalized Weyl algebras. These generalized Weyl algebras, they were introduced by Bavula in 1983, and he has been studying these algebra since that time, so he has a lot of papers about them. This generalization of parametric Weyl algebra is different from generalized Weyl algebras by Bavula, and it was shown by Benkert, Lopez, and Andrus. Actually, Bavula himself has 2 papers about these parametric Weyl algebras. So it was my last remark. Thank you for attention.
Okay. Are there any questions or comments? Okay, let me ask something. Artem, can you go to the last pages of the slides, please?
To the last?
Yeah.
To this one?
Probably the last but one then. Where you talked about the graded identities and so on for these algebras. Yeah. This conjecture clearly it is open, but for these Z-graded identities, there was some movement in last years, namely the same result holds in positive characteristic, but okay, not in your situation when the field is infinite. And the point is that it turns out essentially you have to consider only multilinear polynomials, even in positive characteristic, as long as the field is infinite.
But you consider here graded, Z-graded identities.
Yeah, graded identities. I do not know whether in the ungraded case something similar will hold.
Okay, very interesting remark. And this movement was done by whom? By you?
In Clodemir.
Together with Clodemir. Okay.
Yeah. So I do not know. It might be interesting to have a look there and see whether something similar cannot be used in the case of finite field. I doubt, in fact. When the field is finite, I doubt it will be sufficient to consider multilinear polynomials.
Well, here probably it can be. Well, I've got to think about it, but probably it can be done in case of.
Well, I simply don't know. I doubt if in the case of finite fields you can consider only multilinear polynomials. Since when the field is finite, you'll get some identity that depends essentially on the characteristic.
Yeah, but okay, I've got to think a little bit about it. So this paper, is it in archive or maybe it's published?
Yeah, it was published. If you want, I send you later on.
Okay. Yes, please.
The
Yes.
PDF.
It will be interesting to have a look. Yes.
Okay. Are there any comments or questions?
Actually, I also got one question. It's not that easy to interact because we are kind of here taking care of the sound, but I would like to make my question and then I can hear the answer. Artem, please, could you clarify a little bit technically what is the connection that you mentioned between the hypothesis that is on that slide and something about additive base as that is known, as I understood? What the connection between the hypothesis that should be proved and the base? Just a
which
second,
conjecture?
I'll be back.
Okay, can you hear me? Between which conjecture, which is on this slide or which was written at the end of my talk, which is on this slide?
Yes, this slide.
Well, about this conjecture, I actually don't know a lot. I mean, I just know that, of course, multiplication in with algebra is it has very nice formula, and actually there is very nice method how to multiply several basic elements, like very nice rule. Maybe let's put it in this way. But apart from it, I don't know a lot about this conjecture. No. I don't know how it's possible to prove it. I mean, just this idea about Z-graded identities. Yes, in case of Z-graded identity, it's more or less clear what to do, and it was done. And, this case is more clear, but general case it seems very complicated. I mean, here you even verify that it is a minimal identity. I guess if you try to do it, it's also not so easy to do. I mean.
Okay, and gonna be one more, a matter of curiosity, like a comment and curiosity. Could you come back to the slide 14 with the one Lie-Bransky result about characteristic 2 infinitely based Lie algebra, that stuff? Yeah, you made some interesting comments about this corollary. Did I get it right that actually Bransky was the first to?
Well, once again, Bransky considered.
Wait a little bit.
Yeah.
Just don't say what we need to figure out. I need to hear your answer. Okay,
of
just
course,
give me a minute.
Bransky was first, but he was first not about this corollary, of course.
Yeah, try to say that.
Bransky considered the case of Lie algebra of 2 by 2 matrices over infinite field F. Okay. Of characteristic 2 and described its basis. And it was published in his thesis, and he didn't publish it as a paper.
Okay. I got it. Bransky was the first to...
Yes. Then I wrote a preprint, put it in archive about the same subject. I never submitted it to any paper because I had a feeling that maybe somebody did it, and then later Bransky told me that he did it. And then, but I mean, still Bransky didn't publish it. Then Bransky published this survey about weak identities. He mentioned his result in explicit form there. He mentioned my name also, that I also did it like independently and using different methods 30 years after. So essentially speaking, that's it.
Yeah, that's okay. That's what I wanted to clarify. Thank you.
Okay, and probably I can add a couple of words about that conjecture of Razmislov. It seems really very hard, a very hard problem. And as far as I recall, there were a couple of papers by Mishchenko, probably. Yeah, by Mishchenko, but not for answer. So most likely it should be true. But it seems very hard, really.
But then I have a question. Is it known that, let's say, it's identity of minimal degree?
I think yes.
Okay. Because
no, you see, it should be minimal degree. Since if you have an identity of degree 4 in the Lie case, it should imply solvability. Yeah, really, every Lie polynomial of degree 4, multilinear Lie polynomial of degree 4, you consider simply the diagrams. Every identity of degree 4 implies solvability of some degree. And it can be seen easily by decomposing the Lie multilinear element of degree 4. The dimension is very low. You have dimension 6, so it is easy to decompose a sum of two irreducibles. So it goes straightforward. And so this algebra is simple, so it is not soluble. And it cannot satisfy any identity of degree 4. And I think it is, but I'm not sure of this. You have to look for Mishinka's papers. That this is the only one in degree 5, but I'm not quite sure. Okay, are there any other questions, or we can close the first session for today?
I think we can close.
Okay, then let me thank Artem once again, and also all the speakers of this morning. We resume at 1:30 Brazilian time or 8:30 Italian time.
Yes, exactly. See you soon.
See you soon.
Okay,
Bye.
see you.
Bye.